Now we're into 8.5, which begins on page 641. And we begin with theorem 814. Which is the ratio test. And this one you're going to use a lot. So let's look at this carefully and pay attention and do some examples, because the ratio test does get used quite frequently and is often very effective. Okay, so again, what is our situation? We are looking at a series, an infinite series of a sub k's, and we're trying to figure out whether it converges or diverges. And we're going to look at R being the limit as k goes to infinity, R for ratio, of the successive terms. The k plus 1th term over the kth term, the next term along the line. So you're basically going to make a fraction of what's going on when the sequence goes to the next term down the line in general. And we're going to take the limit as n goes to infinity for that. So that basically means we already know, for example, that we're only considering using this test to determine if a series converges or diverges, because it already sort of got no clarity from the divergence test. So we already know the terms go to 0. So what we're looking at here is how quickly they go to 0, because we're basically taking the limit of the next term down the line and seeing if it is significantly smaller than the term right before it. If it's not going down very quickly, that might suggest that it diverges. If it's going down more quickly, that might suggest that it converges. So we're going to take the limit of this ratio of successive terms and consider what we get. And here's what the theorem tells us. 1. If 0 is less than or equal to r, which is less than 1. So if r is some number that's below 1, like 1/2 or something like that, well, what would that indicate? That would indicate that the next term down the line is half as big as the one before it. So that would suggest that the series is shrinking in term values pretty quickly, kind of like a geometric series where it's 1/2 each time. You're basically going to imagine that in a geometric series, it converges if you're multiplying by a number less than 1 each time. But if you don't have that simplicity, then you could say, well, what if basically the limit as you head off to infinity is that the term following the one before that is half as big, or 80%, or 90%, or some number less than 1. That basically means that we can look at the series like it's a geometric series where the ratio value is less than 1. And so if r is less than 1, then the series converges. So you're in the middle of a class, so you just stay downstairs.
Oh.
Thank you.
What happened?
Stevie? No, go downstairs. I'm in a class right now. Sorry for the interruption. Okay, similarly, if the r value is bigger than 1, well, what does that mean? That means that the next term down the line as a ratio is larger than the one before it. So if r is bigger than 1, including if r is going to infinity or something really aggressive like that, then the series diverges. So the only case left to consider is that what if r is equal to 1? So this basically means it's kind of like they're staying constant, but we don't know. And that may be more confusing, but basically in this simplest format, that means that the test is not going to be helpful. So then we say then the test is inconclusive. Which basically means, that we can't, this test doesn't help us determine whether it converges or diverges. Okay, so this is called the ratio test. And the way you apply it is you make a new limit of the k plus 1th term over the kth term. You take the limit as at k goes to infinity of that, and you look at the number you get. And if it's less than 1, or if it's bigger than 1, you're able to draw a conclusion by this theorem, by this ratio test. Otherwise, this test was not helpful. That's the conclusion here. So let's, we need to see an example of this in action. So I'm going to, let's just look at the first one. So there's example 1A on page 641. So it says to use the test to determine whether the following series converge, and we have the series as k goes from 1 to infinity. So this is an infinite series of 10 to the k divided by k factorial. So a couple of things to take note here. We haven't used this for a while. I can't remember when we used it last. The factorial notation. So what does factorial mean again, as a reminder? If you have a number with a factorial, that means that you take that number, multiply it by the number 1 less than that, and keep doing that, counting down until you run out. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. So hopefully this is something that looks somewhat familiar and you remember this from previous work, because the book's not going to really explain it at this point, thinks you know it. But there's a little example as a reminder. Okay, and so when we have that, the thing to point out is that k factorial only takes integers. So when you have a factorial included in your formula for your terms of your series, you will not be able to write that as a function. So for example, if I tried to write f of x was equal to 10 to the x over x factorial, this is undefined. This doesn't work. Because you can only take a factorial when you have whole numbers so that you can count down and things like that. And so since that's the case, and we can't make a function out of the formula for the terms, that means we can't use the integral test. Because the integral test, we would take the integral from 1 to infinity of the function for those terms. But we can't do that when you have a factorial. So I'm pointing this out because factorials are a big indicator real quickly that you can't use the integral test and you're going to be doing something else. In this case, we're looking at the ratio test. Now let's look at the big idea here. What if we were trying to do the divergence test? So then we would say, hey, let me take the limit as k goes to infinity of the terms themselves. But again, when we have this factorial thing, that's going to mess some things up because this is of the format of an infinity over infinity. But because k is not a continuous function, then we don't have anything like the derivative. We can't use L'Hopital's test, right? So what we're seeing is that as we now get to this ratio test, they're introducing a problem with a factorial in it. And the good reason for that is that, like all of our earlier tests, don't really work. So we really, this is a good example where if we think about the series that we're given here, it really does all of a sudden make all of the work that we did up to this point for our tests unusable. Now, again, let's just try to visualize what's going on here a little bit, and then I'll throw the test in, just to get used to the notation. So if k is a 1, I have 10 over 1 factorial, which is 1. If k is a 2, I have 10 squared, which is 100, over 2 factorial, which is 2. If k is a 3, I have 1,000 over 3 factorial, which is 3 times 2, or 6. If k is a 4, I have 10 to the 4th, which is 10,000, divided by 4 factorial, which is 4 times 3 times 2, which is 24, because it's 4 times 6. So on the top, we see a number that's growing up as powers of 10. That's exponential growth. And we're used to the idea of exponential growth just being runaway growth, very, very big and powerful. And like already we're up to 10,000 over 24, 1,000 over 6, like huge numbers that are getting bigger as we are going down this list here. So not only are we adding very large numbers to our total, but the numbers we're adding are growing larger. So this really kind of looks like the top is going to dominate. However, I'm pointing this all out because in the end it doesn't. The k factorials, when you allow k to go to infinity, exceed exponential growth. Factorials grow really, really much, much faster. And you can go back to the growth rate thing to sort of kind of see this coming a little bit. And so as we're trying to develop our intuition for sort of what's dominating and what's going to happen, I'm going to just, as we first see it in our first example, point out to you that when you see a k factorial to determine what the terms of a series are, that's going to grow immensely in the end as you go to infinity, much faster than pretty much anything else. So how would we evaluate this? So then I'm basically going to say that we would want to try the ratio test, because none of our previous tests will apply here because of this factorial. And to do that, we need to find R by taking the limit as k goes to infinity. And so what are we supposed to do? The k plus 1th term over the kth term. So you're going to make a fraction in which in the top of the fraction, you use the formula, but you put in k plus 1 instead of k. So this would be 10 to the k plus 1 divided by k plus 1 factorial. Then you divide that by a sub k itself, which is just the exact same formula, 10 to the k divided by k factorial. So we are often looking at series in which the terms of the series are a fraction. So if you're using the ratio test and the terms of your series are a fraction, then when you take this, when we try to find this R value, you're going to be taking a limit of a fraction divided by another fraction. And so usually pretty quickly people see this pattern and they will flip the bottom fraction in order to multiply it by a top to simplify that. So this looks like this. R is equal to the limit as k goes to infinity of 10 to the k plus 1 divided by k plus 1 factorial times the flip of the bottom would be k factorial in the top divided by 10 to the k in the bottom. Questions about that manipulation? Okay, so to try to simplify and evaluate this limit, because we need to find the R value and see if it's bigger than or less than 1, we would need to simplify this expression. So the first part is pretty straightforward, hopefully, that if I have 10 to the k plus 1 and I divide it by 10 to the k, then this cancels with that, just leaving 10. Because this is like 10 squared over 10 to the first, or 10 to the third over 10 to the second, or 10 to the 101 over 10 to the 100. And when you have exponents, you subtract the lower power from the upper power. And in this case, that would just leave 10 to the first power, which is 10. Then the question is, how do I simplify k factorial divided by k plus 1 factorial? So if you've worked with factorials, you may know the answer to this already, but let's look at what this means. K factorial means k times k minus 1 times k minus 2, all the way down to multiplied by 1. That's in the top. So k plus 1 factorial means instead of starting at k and working my way down, I start at k plus 1. So that would be k plus 1. And then if I go down 1 from that, then I get k, and then I get k minus 1, and then I get k minus 2, and I go all the way down until I get to a 1. So what we'll see here is that when you make a fraction of a k factorial and a k plus 1 factorial, that the only thing that's left is the k plus 1, because all the other factors cancel out. So that means if I reduce this, basically the k factorial cancels out the factorial part of k plus 1 and just leaves the k plus 1. So this would give me a 10 in the top and a k plus 1 in the bottom. Now again, I'm taking the limit as k goes to infinity. So after this simplification, I have a k in the bottom that's still going to infinity, but all I have in the top is a 10. So if the denominator is going to infinity and the top is just staying at 10, that ratio has a limiting value of 0. So in order to apply the ratio test, I set up an R equal to the limit as k went to infinity of the k plus 1th term divided by the kth term, and that turned out to be 0. Any questions about how I did that, or about this simplification of the factorials or anything?
I have a question about when you simplify the factorial.
Yes.
So when you're doing k plus 1 factorial, why is it k plus 1 times k and then times like everything else?
Okay, so let me use a specific example and see if that helps make it more clear. Let's say instead of k, I had 10. So if I had 10 factorial in the top, then k plus 1 would be 10 plus 1 factorial in the bottom, which would be 10 factorial over 11 factorial. Does that make sense?
Yes.
So k plus 1 is just one more than whatever k is, like 10 versus 11. So that would mean in the top, I have 10 times 9 times 8 times 7 down to 1. And the bottom, I have 11 times 10 times 9 times 8 times 7 down to 1. And so because after from k plus 1, I drop down to k and continue dropping down, then everything after the k plus 1 is the exact same thing that's in the top, and I'm just left with the one in the bottom.
Yeah, that makes sense.
So that means whatever k plus 1 is, whether it's an 11 or whether it's 1001, whatever it is, after you simplify it with the other factorial, you're just left with that number in the bottom.
Okay, thank you.
Yeah, good question. Other questions about anything here that I can explain better or elaborate on? Yeah, definitely as you get drowned in all these letters, which is very easy to do, and you're trying to say, what the hell are they talking about? It's a very good practice to sometimes just put in a specific example and just say, well, what if I had this value, or what if I had, this particular number here, just to help make this easier to follow along. Okay, so to use the ratio test, we set up the limit as k went to infinity of this ratio of successive terms, and in this case, we got a 0. So then we would say then by the ratio test, so what would we conclude? Anybody able to see? Does this mean that the series converges or diverges or what? Here's the ratio test up here. So based on those three choices, what do we say? Can anybody offer that up?
It converges.
Converges, very good. And the idea is that if R is between 0 and 1, less than 1, but could be equal to 0, then the series converges. And what is this actually, if we look at it, as I was mentioning before, when we wrote out the first few terms of this series, the top was becoming 100, 1,000, 10,000, 100,000. It seemed to be growing so quickly, while the bottom was like, 2, 6, 24. It didn't seem to be that significant. But not only does the bottom go to infinity faster than the top, the ratio of successive terms ends up being 0, meaning that we're not even saying that later it's like the top is only 80% of what came before, or only half of what came before. Literally, the bottom grows so much more quickly that these terms go to 0 actually very fast once you get past a certain point. And that's what I was trying to recommend you begin thinking about, that the power of the k factorial is huge. It grows so quickly. Basically, you keep multiplying by a 10 in the top of the fraction. But as soon as k is bigger than 10, then you're multiplying by more than 10 in the bottom when you have k factorial. Once you get to 11, when k is 11, then in the top, you multiply by another 10, but in the bottom, you multiply by 11, and then a 12, and then a 13. So you end up multiplying by a number in the bottom that's getting bigger and bigger than the 10, whereas on the top, you just keep multiplying by 10. And that causes the bottom to grow eventually drastically faster than the top. Anyway, something to think about to try to develop your intuition. So then by the ratio test, the series converges. Now again, we don't know what it converges to. This is not telling us a value, but it's simply C or D, converge or diverge, and in this case, it converges. So this test is really, really crucial. and you will use it a lot. So it's good to sort of practice it, do lots of examples of those, try to see how it works. Often it's the one you want to use when you have this factorial in here, because the factorial doesn't really work as a function. It only works as something with nice integer values. But when you set up a ratio, it cancels very nicely. And the factorial ends up going away, leaving you something that you can take the limit of. And so when you see factorials, that's a good suggestion that maybe the ratio test is involved. Okay, so I'm going to go up here and add a test, a ratio test. Keep doing that. Ratio test is a very important one, gets used a lot. It's probably your #1 used test, unless it's something like the p-series where you can just look and see that it's obvious. So let's move on to the next test because we still have quite a few to look at and time is not on our side. And just trying to save a little writing is making lots of extra work. Such is life. But I'm stubborn. Okay. So next test on the list. Another theorem on page 815. I'm sorry, on theorem 815 on page 642. And this is called the root test. So the root test has us do something similar than what we were just looking at. Let have an infinite series of a sub k's with non-negative terms. So I'm going to have non-negative terms, and notice the r value before had to be non-negative as well. So then it says, and let rho equal the limit as k tends to infinity of the kth root of the terms. So for the root test, you basically take a root, the kth root of the terms. And based on what happens when you take the limit as k goes to infinity of the kth root of the terms, we try to determine whether the series converges or diverges. So it's basically those kind of three possibilities that we looked at in the ratio test. If 0 is less than or equal to rho is less than 1, the series converges. If rho is greater than 1, it diverges. And if rho is equal to 1, you can probably guess the test is inconclusive. It's not an E, it's a rho, which sometimes looks like a P. It's like a Greek letter. I'll try to be more clear with it in a sec. So here's my attempt to draw it as accurately as possible. Maybe that's a little too curvy, maybe more like this. Nah, that's not right either. Yeah, in the book, it kind of looks like weird italic small p. So yeah, but it's pronounced row. Let's try this one more time. Maybe that's not bad. And it's like pronounced row. R-O-E might even be how it's spelled if you spell it. I'm not sure. Can I say I'm a math teacher? So it's something like that. But yeah, you say row. Yeah. So what does this have us do? Well, this has us take a limit after we've square rooted something. So you can kind of imagine that how much easier is it to take limits of expressions if they have a root on it, and the root isn't even a straight square root, it's a kth root. So it really basically only makes sense because there's a big K power somewhere that we want to get rid of. Then it makes sense to take the root test because you have terms that are somehow raised to the kth power, and you have to see if that happens, if that's going to cause it to get bigger or smaller in a way that diverges or converges. So without going into it too much, the best thing to do is just look at an example. So let's take a look at an example here to see what this allows us to do. And so this is example 2 for the section, which is over near the top of page 643. So let's say they give us a couple. Let's look at A. So again, it says use the test to determine whether the following series converges. So all we're doing at this point now is just converge or diverge, C or D. So we have the limit as K goes from 1 to infinity. And in this case, we have a nice rational expression, 4K squared minus 3 over 7K squared plus 6. All raised to the power of K. So again, we could like try to put out the first couple terms of this. Yeah, why don't we do that? Just as an exercise to remind ourselves that as these formulas get big and ugly, we can still try to ground our understanding a little bit by just maybe writing down what they mean. So if K was a 1, then I'd have 4 minus 3 on the top, which is 1, and 7 plus 6 on the bottom, raised to the first power. So that would be 1/13. Put the power up there to remind us. And it's going to get worse pretty quickly. If K is a 2, then on the top I have 2 squared is 4 times 4 is 16 minus 3 is 13. And on the bottom, I have 4 times 7, which is 28, plus 6 is 34. And that would be squared, and etc. So this is, you know, kind of an ugly looking series. But we're supposed to figure out if this thing converges or diverges. Well, we could note that the bottom has numbers that are bigger than the top. So I do have fractions that are less than 1. But I'm not able to use the divergence test just on that, because then those are then raised to a bigger and bigger power. And when you take a number less than 1 and you raise it to a bigger and bigger power, then that number gets smaller, like 1/2 to the third power is 1/8. Anyway, so if you try to sort of think this through, it gets a little uncomfortable because of this power K. So here's the thing to note for the big picture. This is making everything harder. So this, since it's a power of K, suggests try the root test. Because since you're raised to a power of K every time, you can make that go away by taking the kth root, which is what the root test does. So that's how you look at that. So then we say let rho equal the limit as k tends to infinity of the kth root of a sub k. But in this case, a sub k is just that stuff right there. 4k squared minus 3 divided by 7k squared plus 6. And so pretty quickly, the nice thing about this is the root cancels the power. That's why we're applying this test. So I then have the limit as k tends to infinity of 4k squared minus 3 over 7k squared plus 6. So that makes the power go away, and that means we have a limit without that power getting in the way. So does somebody think they could evaluate this limit? Anybody want to offer up a suggestion for what you'd get? So I see a text sent in of 4/7, which is perfectly correct. Well done. And again, how would we know that? Chapter 2 work. This is a limit of a rational expression, and its degree of the numerator and the denominator is exactly the same. So there's kind of a balancing act here. And so when that's the case, the ratio of the leading coefficients ends up being what you get for your limit. You could also divide the top and the bottom by k squared to see that algebraically, if that's still hard to visualize in advance. But yeah, Timothy is correct. So we get 4/7 here. And so that is this rho value that we were tasked to evaluate in using this. And then again, just like with the ratio test, if that number is between a 0 and a 1, not including a 1, but less than 1 specifically, then we get convergence, which 4/7 is less than 1. So that's what we get. So therefore, the series converges by the root test. And again, this doesn't tell us what the series would converge to. It just tells us that it does, that it converges. Questions, comments, discussion?
I have a quick question.
Yes, ma'am.
So with these types of problems, like, will we be asked to determine like where it converges to, or just say D or C?
Well, that's a good question. Most of the time, it will just be D or C, because most of the time determining what it converges to without just doing that numerically would be very, very challenging. However, the one big exception for that for us is that an infinite series that converges in which we can find the actual value is the geometric series. So that's one of the reasons we focused on the geometric series, because if it is a geometric series, then we have a little formula, a over 1 minus r, that tells us what it converges to. And in those cases, it's not only, could it be expected that we would find the value it converges to, but it's an easy formula. So those kind of problems are nice. So if they're telling you to find the value it converges to, there's a good likelihood that it's a geometric series and that simple formula will do that for us. But if not, most likely they're just going to say C or D. Does that make sense?
Yes, it does. Thank you.
Good question. Other questions about that? So yeah, as I was mentioning before, a lot of these problems will be kind of like true or false, meaning that there's just a T or an F, but in our case it's C or D, converge or diverge, and we have this variety of tests that we're supposed to use to try to figure that out. Any questions about the root test before we look at the next test? Okay. So I'm going to try to erase. So let's leave the test that we have so far. So these are the ones we have so far that are kind of formulaic like this, where we figure out a particular limit, an R value or a rho value, and then we sort of compare those to a 1. Is it less than 1? Is it bigger than 1? To see what we get. So that's with the ratio test and the root test. You get this R value, you get this rho value, you compare it to 1. The P-series test is pretty much just 1 over k to a power, and is that power bigger than or less than a 1? The integral test is a little bit more complicated because you have to be able to evaluate an integral from 1 to infinity of a function version of the series. Then you also have something that has to be writable as a function. And then the divergence test is the simplest because you just say, hey, are the terms going to 0? Let me take the limit. If not, then it must diverge. So with all of these in place, we start to, as in the past, accumulate results. As you use these, you start to get things where you can say, hey, I believe that converges or that diverges pretty quickly. So consider, this is all to motivate our next test. Like if I had the series of 1 over k to the 5th power. So what are you guys looking at that? What do you guys think? Does that converge or diverge? There's questions about which test, do we have to say which test we use? How many tests do we have actually? So we're about to do 816, which is a comparison test. There's a limit comparison test, which is 817. Then in 8.6, we have an alternating series, which has its own test called the alternating series test. So we will have 3 more tests. Looks like that totals, at least in this format, to 8 tests in total. Do you have to say what test we use? You'd only need to say what test you use if you have a problem that asks you to justify your steps or show your work. So you can think that the simplest problem would be like a true-false statement. It would be a C or D problem where it shows you a problem like this, and then it says C or D, and then you just circle your answer for which one you believe. That would be the simplest, and then obviously which test you use is irrelevant. You could use a Ouija board. It would be up to you. Whoops. However, the other thing is it could say determine whether it converges or diverges and show all supporting steps to receive full credit. And then you would need to show which test you applied. You would have to show it applied, etc. So looks like we'll have a total of 8 tests, and you may or may not need to say what test you used depending on the type of problem you're given. Certainly on the computer, they can't really do that. They can't really ask you which test you used. So anyway, so having said that, let's get back to this, this problem that we're considering. Do we believe this converges or diverges? C or D? Any opinions?
Converge.
Converge, and are you willing to try to justify that?
P-series test.
Series, exactly. So this is a power function with a p-value of 5, and the p-series test says if p is anything bigger than 1, including like 1.0001, anything at all bigger than 1, then it converges. This is a 5, which is bigger than 1. So it converges. We would choose that. And then if we were asked to justify, we could say by p-series test. All right. So we now have tests and results that we can start to sort of imagine we could accumulate or envision in our mind. So now let's say instead we were looking at this.
Converge.
So how do we get a feeling or belief that this converged?
The bottom part is bigger than the first one.
Yeah, that's a great way to say it. Thank you. So the first thing I would point out is that basically these are the same, right? Here you have a k to the fifth on the bottom, and here you have k plus 1 to the fifth on the bottom. Adding 1 to k still doesn't change the fact that you have fifth power of k on the bottom here. And even more specifically, by adding 1, the terms on the bottom have a larger denominator than the terms on the top, or the terms in the first one, making the value of the fraction smaller. What I would basically say is that for all k, 1 over k to the fifth is bigger than 1 over k plus 1 to the fifth. And then this is k like integers, positive integers, natural numbers. So I'm going to write that with the math symbol. For all k, a member of the natural numbers. Again, that means 1, 2, 3, 4, 5, 6, something there. If you add 1 to k before you raise it to the fifth power, you're just going to get a bigger number. And if the bottom's bigger, then the fraction is smaller. So this basically means that we have terms of a series that are smaller than terms of another series that we already know converges. So if the terms of this series are smaller than a known convergence series, well, then it has to converge as well, assuming they're all positive. So this idea that these are like this, but just smaller and therefore must also converge, we create a test out of that called the comparison test. So that's our next test, and this is the exact idea for how we can use it. So the comparisons test basically says, if I have terms smaller than another test that I already know converges, then I can conclude my new series converges. Or similarly, if I have terms of a new series that are bigger than another series that I know diverges, well, if your values are bigger than a divergent series, your series must also diverge. So this is theorem 816 on page 643. And it's the comparison test. So it says that we have the summation of a sub k's, and we have the summation of b sub k's. So we have two different series with positive terms. So then we're going to have two possibilities. One, if 0 is less than or equal to a sub k, which is less than or equal to b sub k, this would be for all k, of course, and the series of b sub k converges, then the series of a sub k's also converges. So this is what we were just looking at in an example. We knew, in our case, the b sub k's was the 1 over k to the fifth, and 1 over k plus 1 to the fifth is always less than that. So that's our a sub k's, and we know that the first one is convergent, and our new one is less than that, so it also converges. So if you have a series you're considering of a sub k's, and every term is less than another series of b sub k's that you know converges, then a sub k has to converge as well. And then similarly, we can do this the other way around. If 0 is, so these are positive, is less than or equal to b sub k, which is less than a sub k. Whoops, sorry. So I think these should be strictly bigger than 0. Well, on this case, I did the wrong one, of course. So, if we have a new series of a sub k's, and each term is greater than or equal to some other series b sub k, and we know that the series of the b sub k's diverges, then our new series of a sub k's must also diverge. So we did just look at an example as the one I did to try to warm up to this idea. But let's look at another example that we could apply this to. So let's say maybe we consider example 3, which is on page 644. Okay, so this says, at least in part A, and again, determine whether the following series converge. And on this one, we have the summation as k goes from 1 to infinity of k to the third over 2 k to the fourth minus 1. So here's the thing about the comparison test. They're not going to give you both series. They're just going to give you a new series. And you have to look at it and kind of try to determine whether you think it converges or diverges or not. And the normal idea would be is that you would look at it, and if you developed a suspicion, it might be because it looks like a series that you've worked with before, where you know that that one converges or diverges. And if that's the case, then maybe you can make a direct comparison to that one in order to do the problem. Does that make sense? So what does this series look like if you just thought of it in your mind in as simple a way as possible? Well, as we've learned when taking limits and things like that when you have a rational expression with just powers on the variable, the leading powers are the only ones that matters. So this kind of looks like 1 over k, because the power in the bottom is 1 more than the power in the top. Again, we can ignore the constant multiple of a 2 here, because that would just be pulled outside and wouldn't matter. So this kind of looks like 1 over k. It's off by a little bit because there's this minus 1 here. So does the series of 1 over k converge or diverge? What do you guys think? Anybody willing to offer up a suggestion?
Would it converge?
1 over k. So 1 over k is, would it help if I told you that we've given it a name? So the series of 1 over k is called the harmonic series. That's 1, 1/2, 1/3, 1/4. This is the harmonic series. So it was a good guess, but no, this diverges. In fact, the series 1 over k, the harmonic series, we have a theorem that specifically states that this diverges because this is such a crucial one that we want to work with. So if we look at this expression and we say, well, it kind of looks like 1 over k, and I know that 1 over k diverges, then I would be able to use the comparison test if I could compare these terms to the 1 over k series, and they would be a little bit larger. Now, unfortunately, if I multiply the 2 times the k on the bottom, that makes it half as big, but basically we can still get there anyway. So let me show you what I would do. And this is probably what the book does, but I never look at what they do when I do their examples for you. So here's what I could do. If I had that motivation, then I could say that k cubed over 2k to the 4th minus 1 is always going to be bigger than k cubed over 2k to the 4th. Again, this is for k bigger than or equal to 1. So this is true because the denominator of the left term is larger when compared to the denominator of the right. Is smaller because we're subtracting 1, making the value of the fraction larger. Because you have a smaller denominator with everything else staying the same, means you have a larger fraction. And the summation of k to the 3rd over k to the 4th times 2 is equal to 1/2 the summation of k to the 3rd over k to the 4th, which is equal to 1/2 the summation of 1 over k, which diverges. So this one diverges, which means that since this one is bigger, this diverges by comparison. So basically, we are saying in this problem that this diverges because we can compare it to this, which we can quickly see diverges. So this diverges because it's just a straight multiple of the harmonic series. So it diverges, and the terms of the series we're looking at are larger than the terms of this divergent series. So by the comparison test, it also must diverge. Questions, comments, discussions about that? As I see, we are 4 minutes beyond time with that last problem.
Yeah, Professor, so in general, how would you know what to compare it to?
Well, that's why I said we don't have a way to know that in advance, because it's based on having a sense of accumulated results and having used the earlier tests, these 5 tests up here, enough to have some expectations of what converges and diverges from those, so that we can then say, hey, this looks like one of these ones I've done before. Now, this was the perfect example. I told you to say what this looks like, right? I said this looks like 1 over k, but then the only person who was willing to take a stab at whether they thought that converged or not thought that it converged when it didn't, it diverged. So obviously the comparison test will make more sense when you've got some more tests under your belt and you've done more of these and developed some sense of it. And keep in mind, we are looking at one of the later tests in 8.5 when you guys haven't really even done the 8.4 problems in quantity yet to get this comfort level. That's the problem always with covering multiple sections on one day, is that a lot of times the second section depends on comfort with the first one, which you just talked about during that same session. I've always had troubles with these 2-hour, 2.5-hour formats because you have to cover a couple sections, and that's really hard to do for this exact reason. But nonetheless, hopefully the comparison test will feel more comfortable and make more sense in how to use it when you've done a bunch of other tests on quite a few problems and you're starting to get a sense of which kind of series converge and which kind diverge. Then it's easier to make a comparison later to one that you did before.